This video looks at the national grid and how it uses transformers to provide electrical power to the United Kingdom. We are all going to describe what the national grid is comprised of and explain how step-up and step-down transformers are used to make the system very efficient. Sets C, A and B will then stay on the line for the higher tier content, which is to explain how transformers are designed for their function. For this, you need pen and paper. The national grid, and a cartoon of the national grid is on the screen now, is used to distribute electrical power across the country. It is a system of cables and transformers that connect power stations to homes, workplaces, and public buildings all around the country. The electricity or the electrical power may be created using traditional methods, such as burning coal, oil, or natural gas in a fossil-fueled power station, or using renewable methods, for example, wind turbines. When transferring the energy through the wires or through the cables, and those cables are what you can see here moving between the pylons, the process needs to be as efficient as possible. You can imagine when we are transferring power across the entire UK, then those cables are going to be going for many, many, many kilometres. Any power that is lost is a loss of money and also a waste of the fuel that is being used to generate the electricity. So the energy suppliers want to minimise any energy being lost as a store of thermal energy. If there is a high current inside the cables, this means there's going to be more friction between the electrons, which are the charge carriers, and the wire, and therefore more energy is going to be lost from the wires as a store of thermal energy. If the wires warm up, then not all the energy is being transferred electrically, but some of us is being used as a thermal energy store, and this means it is less efficient and energy is being wasted. So if it is if there is high current, the cables will get warmer because there is friction between the electrons and the wires. This means the most efficient way to transfer the electrical power along those cables is to have low current. And that's what's being represented at the bottom here. We can see there are fewer charge carriers moving across that same distance. Now we have to ensure that there's the same amount of energy being transferred every second. And energy transferred per second is the power, represented by the P here. So this power, this P, is the same throughout the entire national grid. And we know that we want to decrease the current in the cables so that we make the process as efficient as possible. If we decrease the current in the cables, we therefore need to increase the potential difference in order to make sure that the power stays the same. So we now come to our first multiple choice question. So make sure you pause the video and then answer this question. What is kept constant through the national grid? A, current, B, potential difference, C, power, D, resistance. Pausing and answering. Great, so let's go through this first multiple choice question. What is kept constant in the national grid is the power. The electrical power transmitted is the same throughout the entire national grid. Second multiple choice question, please pause and then answer. If there is a high current in the cables, is it A, B, C or D? Good. So hopefully you've now got a letter A, B, C, D all written down. So the correct answer here is if there is a high current in the cables, the temperature of the cables increases. So it's either going to be A or B. And then we have to think about what that does. So higher temperature means we've decreased the efficiency because we've got a higher store of thermal energy. So the correct answer here was A. Final multiple choice question for now. Pause the video and answer this question, please. To keep the power constant when the current is decreased, the potential difference is A, increased, B, kept the same, D, decreased. Pausing and answering. So let's go through this one. If the power needs to stay constant, because power is current times potential difference, if the current is decreased, the potential difference must increase in order to make sure that that power is kept the same. So in order to change the potential difference across those cables, and by changing the potential difference, we in turn change the current, we use something called a transformer. And there are two types of transformer. One type of transformer is called a step up, and the second type of transformer is called a step down. So let's first look at a step up transformer. On the screen, we have a kind of photo of what a transformer looks like in real life, and then a kind of sketch of what a step up transformer looks like. A step-up transformer is designed to increase the potential difference and therefore decrease the current. So we use a step-up transformer to move from the power station to the cables, because we know that in the cables we want to have a low current. So step up, the up always refers to what we're doing to the potential difference. So we are upping the potential difference in order to decrease the current. Now, once we get to the homes, those cables are connected to the homes, having a really high potential difference would be very dangerous to the people living inside that home. And so that means to go from the cables back to the homes, we use a step down transformer. Now, what a step down transformer does is it decreases the potential difference, making it safe to use in the home, and therefore, as a result, the current will increase. So the safe value for the potential difference that we use in the homes in the UK is 230 volts. Things like laptop chargers often have built-in transformers or step-down transformers, and they reduce that potential difference even further to make it safe to use on the devices such as your laptop. So we can see that this is able to decrease that potential difference even more to make it really safe. So we're now going to come to another multiple choice question. This one is about a step up transformer. Can you pause the video and answer this question? So a step up transformer, well, the up always refers to what the potential difference is doing. So that means the potential difference has increased. So we're interested in either B or C. And then we have to work out what has happened to the current. Well, if the potential difference increases, the current will decrease. So the correct answer here is C. Can we pause the video and have a go at multiple choice question 5, which is talking about a step down transformer? Good, so the step down transformer, as we know, the step down transformer, the down refers to the potential difference. So we want to be looking at a decrease in potential difference. So it's either going to be A or D. Well, if the potential difference has decreased, it means that the current has therefore increased. So the answer here must in fact be A. We are now going to go through a model example for everybody, so all sets. And the question we are going to look at is this. The national grid includes step-up transformers. Explain why. So a model answer here would look like this. A step-up transformer increases the potential difference across the cables and decreases the current. This reduces energy losses in the cables, which increases the efficiency of the transmission of electrical power. Okay, if we are doing in foundations here, if we are in D and E sets, we can now move on to the homework straight away. If we are in sets C, B or A, please stay on whilst we go through the higher tier content. So we have just learnt that a step-up transformer is designed to increase the potential difference so that we can lower the current. It's important to have low current in the cables to reduce any energy losses from the wires and therefore making the transfer more efficient. So we know that we want to keep the electrical power constant throughout the entire national grid. And so when we use our step-up transformer, we want the current to be as low as possible, and therefore we have our potential difference, which is increased in order to maintain that power. And to do this, we use a step-up transformer. So let's now look in a little bit more detail at a step-up transformer. Any transformer is made up of two coils of wire, a primary coil and a secondary coil, and then you have got an iron core in between those two. And really important that we use iron, because iron can be easily magnetized. For a step-up transformer, the primary coil, which is the input coil, has fewer turns, that means fewer coils wrapped round, than in the secondary coil. So our input coil, our primary coil, has fewer turns than our secondary coil, which is our output. And we already know that the step-up transformer has a larger potential difference at the output, so there's going to be a larger potential difference at the secondary coil than there is at the primary coil, which is our input. And you have now also just learnt that you have got more turns on the secondary coil than the primary. The subscripts S and P stand for secondary and primary here. So how is it that we can actually generate a potential difference across this secondary coil? Well, this is what happens. We input an alternating current in the primary coil. When there is an alternating current in a coil of wire, it creates a magnetic field. Because the current is alternating, the magnetic field is also alternating. Now, this alternating magnetic field will magnetize the iron core. And this means that that oscillating magnetic field gets transferred to our secondary coil. And that alternating magnetic field in the secondary coil induces an alternating potential difference across the secondary coil. And providing that is connected to a circuit, we get current in the secondary coil. We run through that one more time. So we input an alternating current at the primary coil. This creates an alternating magnetic field. The iron core, which is easily magnetized, transfers the alternating magnetic field to the secondary coil, and that induces a potential difference across the secondary coil, and providing the secondary coil is connected up to a circuit, that induces an alternating current in the secondary coil. So we've talked about a step-up transformer. Now we know that, again, the power stays constant throughout the national grid. So when we want to get that power into our homes, we need to ensure that the potential difference isn't too high, because that can be dangerous. And therefore we use a step-down transformer from the cables to the consumers. That could be homes or offices or small businesses. Because we want to decrease the potential difference, the step-down decreases the potential difference. As a result, the current will therefore increase. So let's now have a look at a step-down transformer in a little bit more detail. Now we know that in our step-down transformer, it's the other way around. So we're going to have a smaller output potential difference, which is in our secondary coil, than in our input potential difference. So the transformer looks very similar. We've got a primary coil, an iron core, and we've got a secondary coil. However, notice how the number of turns is the opposite. We have got more turns on our primary coil than our secondary coil. So in this case, we have the number of turns on our secondary coil is less than the number of turns on our primary coil. But the way in which the potential difference is induced is exactly the same. Alternating current in the primary coil, creating an oscillating or alternating magnetic field. The iron core transfers this to the secondary coil, induces an alternating potential difference, which then induces an alternating current at the output. We can work out the potential difference in each coil by using this equation here. So the ratio of potential difference, given by the symbol V, in the primary coil, divided by the potential difference in the secondary coil, is equal to the number of turns in the primary coil divided by the number of turns in the secondary coil. So providing you know 3 out of these 4 values, we can work out the remaining 1. Okay, so we have come to our first checkpoint in this higher tier content. Can you now pause this video, and have a go at answering the first question on a step down transformer? Good, so you should have paused the video and written down either A, B, or C. So for a step down transformer, there are more turns on the primary coil than the secondary coil. So we know that a step down decreases the potential difference. That means we need less turns on the secondary coil. So the answer should be A. Can you now pause this video and have a go at multiple choice question 7? This is a step up transformer. Good, so let's go through this. A step up transformer, we know increases the potential difference. That means we need more turns on the secondary coil than the primary coil, so we should have put B. Now we know that whenever current moves through a wire, there is a transfer to a store of thermal energy and some energy is wasted. This makes the system inefficient because less of the energy is transferred usefully as electrical energy and some is wasted. Now, we know that we can use step-up transformers in order to make the system as efficient as possible, but there can still be a little bit of energy loss. Now, we can work out the amount of power that is lost using the following equation. So power equals I squared R, where I is the current and R is the resistance. So we can see that the current has a really big effect. So if we can make that current as small as possible, then we reduce the power loss as much as we can. Despite this, the national grid is around between 95 and 99% efficient. So sometimes in calculations, we assume that we have 100% efficiency. Now, because we know that this value for the power we try and keep constant throughout the entire grid, by assuming that that power is constant, it means the potential difference times the current in the primary coil must be equal to the potential difference times the current in the secondary coil. So assuming we have 100% efficiency, then we can use the fact that the potential difference in the primary coil times the current in the primary coil is equal to the potential difference in the secondary times by the current in the secondary coil. And again, if we know 3 out of these 4 quantities, then we can work out the 4th one. And just to recap one more time how it is that we can actually induce potential difference from one coil to another. We input an alternating current in the primary coil, which causes an alternating magnetic field. The iron core transfers that alternating magnetic field to our secondary coil, inducing a potential difference and therefore inducing an alternating current. So let's now have a look at some model examples of how we would use these calculations. So the first question we're going to look at here, a transformer has 1,000 turns on the primary winding, that's the primary coil, and has 100 turns in the secondary winding. If the voltage of 250 volts is applied to the primary winding, what will be the secondary voltage of the transformer? So we always have to annotate the question with what we know. So these 1,000 turns are on the primary coil, so that's NP. These 100 turns are on the secondary coil, so that is NS. This voltage of 250 volts, we are told, is in the primary, so that is VP. And then we want to find out VS. So we need to think, well, what equation do we know that has NP, NS, VP, and VS in it? Well, we can use this equation here. VP divided by VS equals NP divided by NS. And then we just have to substitute in the correct values. So we get 250, which we get from here, divided by VS, which we don't know, is equal to NP, which is 1,000, divided by NS, which is 100. So we can simplify the right-hand side, so we get 250 divided by VS equals 10. We then need to rearrange this, so I'm going to multiply both sides by VS. So I get 250 equals 10 times VS, and then to get VS by itself, I divide both times by 10, and I find out that the potential difference in the secondary coil is 25. Let's have a look at another example. So in this example, a transformer has a primary voltage of 30 volts and a primary current of 2 amps. If the secondary voltage is 15 volts, what will the secondary current be? Again, annotating our question. So 30 volts is our primary voltage. And then 2 amps is referring to our primary, so that's IP. And then 15 volts again is referring to our secondary potential difference, which is Vs. So in this case, we've been modelling using this equation instead, the one where we assume 100% efficiency, and so the power in the primary is equal to the power in the secondary. And then we substitute in our values, so we get 20 times by 2 equals 15 times by IS, which is what we're trying to work out. So to get IS by itself, we divide both sides by 15, and then we find out that current is therefore 2.67 amps. So that is how we use both of those equations. I just want to go through one more example that's more involved because it is what an exam question might look like. So the first part of the exam question shows us a transformer here, okay? And it's not explicitly told us what the current across the primary coil, secondary coil, and the current is, but they've labelled it in the diagram. But the first question says, an 18-volt battery could not be used as the input to the transformer, and explain why. This all links to why it is that we are able to induce a potential difference in the secondary coil. So in this case, a battery is a source of direct current, whereas a transformer requires alternating current. So this would be a 2-mark question, and we have to recognise that a battery would not be able to do it because it could not create that oscillating magnetic field. The second part of the question says the transformer is 100% efficient. Calculate the output current for the transformer shown. So again, we need to annotate the question with what we are given. So in the question, we are given the potential difference across the primary coil, here, the current in the primary coil, which is here, and we are given the potential difference in the secondary coil, which is here. And we want to work out the current in the secondary coil. Sorry, there should be an S here, not a P. Apologies. So because they've told us it's 100% efficient, it means that we can equate these. So we can use the fact that Vp IP equals Vs/Is. Therefore, 18 times 2 equals 12 times Is. Dividing both sides by 12 to get Is by itself. And then the answer is 3 amps. Can you now turn to the rest of your homework, going through your knowledge and then answering your questions?